All right, welcome back to the graphs slides. Let's keep on going and finish these up. So there's a bunch of cool graph algorithms that I want to talk to you about. That the first ones, at least, are going to traverse the graph and look for stuff or visit every vertex. So yeah, that's where we're going. Let's start with the first algorithm. It's called depth first search. All right, and so here's the algorithm on the right. And it's like you want to visit every node in the graph, every vertex, in a depth first way. So it's a function that takes your graph. It's an algorithm that takes your graph and then a vertex to start from, and then from that vertex you like branch out and you discover everything that you can reach. Okay? So the idea of depth first search is that you start and you go as deep as you can into the graph until you like try any other possibilities. So the idea is to go as far as possible without retracing any steps, and I'll show you what that means in a second. And then here is the running time. It's like essentially linear. We say v plus e time, the size of v plus the size of e time. That's what that's saying. Cardinality of v plus cardinality of e time, because one of these might be bigger than the other. All right, and the one that's bigger is the one that really wins out when you're doing the big O analysis, but we're not sure which one is bigger, so it's like it's one or the other. Okay, one of the two. So yeah, I think the best way to show you these algorithms is to like not just stare at this all day. Let's give an example, and like let's say that this is our graph G right down here, and we would like to depth first search through this graph G starting at vertex A. Let's say that's like a normal one to want to start with. So let's say we're going to start with that one. A is our starting vertex, and we're going to go as deep as possible. Okay, and so this algorithm involves a stack, and so instead of drawing a stack like this, I'm going to pick a way of drawing it. Like this is how I normally draw like a function call stack, right? A calls B, calls C. Instead of that, or just like that's a model of a stack. Instead of doing it like that, we're going to model it like a list. So A, B, C, where the right side of the list is the top of the stack. All right, so that's how I'm going to write it down here because I need room. So let's do this. Let's watch it work. Let's say we're going to run depth first search starting at vertex A, and we're just going to go through the whole graph, go as deep as possible first. So, all right. The way that this works is we start out with a visited set. So we're going to keep track of where we've been, a visited set. Right now it's empty visited set. And then we also have a stack, an empty stack at the beginning, and we push onto our stack the starting vertex. So A is the one starting vertex, and that's all my stack looks like. It's just A. Okay, so that's how I'm going to draw it. The rightmost thing is the top. I'll draw it like a Python kind of list. Okay, so that's where we start, and then we run this while loop. So while S isn't empty, I have things to visit. I have things to go through. All right. So while S isn't empty, we're going to pop it. All right, and save that into V. So we're popping the top of the stack right now, and it's A that's at the top of the stack. Okay, hope you see that. So we're popping A. So let me start erasing. I'm just gonna like get rid of the closing things because like it's not gonna close for a while. So we're popping off A. We just popped off A. That's sitting in V right now, and we have not seen A. Right? It's not in the visited set because visited is empty. So if it's not visited, that means we have to visit it. So let's go look at it. And so we go and we visit A for some definition of visit. We want to process the node. Maybe we want to print it out. We want to draw it in a pretty way. Just like imagine you wanted to do something with this node. Go do that thing. And then we visited it. So we better add that to the visited set. So now it's there. And then what you do is you push all of its adjacent vertices to S. So we visited A just now, and I'll draw that on the graph. Like that was the first thing we saw. And we're going to push all of its adjacent vertices to the stack S. So we're going to push B, C, and E because those are all adjacent to A. And that's how we're going to discover the graph. All right. So we're going to push B, C, and E. And I guess I'll do it in that order. So push B, then push C, then push E. So the stack looks like this right now. All right. Again, I'm going to draw it like this. B, then C, then E. So E's at the top of the stack. Okay. And then this while loop just keeps going as long as we got stuff to see. So I hope you see how it's going to kind of go through the whole graph as anything that's reachable from the starting vertex. And so, all right, well, it's not empty. Let's pop it. So we're gonna pop the E off the stack now. So there it is. E, we're popping it. Go away, E. We popped you. We have not visited E. It's not in the visited set. So let's visit it, print it out, do whatever we wanted to do with it. add it to the visited set because we've gone through it now. And so it was the second thing that got added. So second node we visited in this graph. And then we'll push all of its adjacent vertices to S. So notice that we're going to push A. You see that? We're going to push A and we're going to push F. It's kind of useless to push A. I hope you see that. It's like we've already seen it. So there's a better way, right? But we'll follow the algorithm right now. We'll push those guys, and so it's F that's sitting at the top of the stack, and we're just back in the while loop. So while S isn't empty, pop the top of it. So F is at the top right now. Pop it off. We have not visited F, so let's visit it. Do its thing. Add it to the visited set. That is the third thing I saw today. And push all of its adjacent vertices into S. All right, so again, I'll push E. I've already seen E, but that's fine. I'll follow the algorithm. I think you can probably see a way to fix this and make it a little bit more efficient, right? And then I'll push B as well. Those are the two things adjacent to F. So now B is sitting at the top of the stack, and I've visited 3 things so far. So all right, just keep on popping. So stack is not empty, so let's pop B off. Bam. Oops. So now we're looking at B. We have not seen B before, so let's visit it. Add it to the visited set. There it goes. That doesn't really look like a B character. There we go. And it was the 4th thing we saw. See that? And kind of like the way we saw it. It was like A saw E, E saw F, E discovered F, F discovered B. If you want to give them credit, I guess. And then we'll push all of B's adjacent vertices into the stack S. So we've got A and D, it seems. So I'll do A. Then I'll push D, so D's at the top of the stack right now, and we're going to wrap around again. So back at the top of the loop, S is still not empty, so I'll pop that D off, and all right, what does that mean? Well, let's check. Have we seen D before? We have not, so let's visit it, add it to the visited set. See how this is discovering the whole graph? So there's D, and we've noticed it. It is thing number 5. We noticed it from B if we want to draw that. So there's that, and we push all of its adjacent vertices into S, and so we'll push B. And all right, though we've seen B, right? And now, all right, we go back to the top of the loop. We're back there. So now we have a lot of popping to do, right? Because we've seen a lot of things. So like we're gonna pop B, right? Pop B off, but we visited B. We pop B off. But we have visited B. And why does the eraser not work? I will never know. Pop B off. We visited B. It's already in the visited set, so we're just going to skip. See that? Oh gosh. I don't want the eraser now. This is too complicated, obviously. Alright. So yeah, we just popped the B off, but we've seen it. We're good. So like we're going to skip this whole thing because it's in the visited set. So we just go right back to the top of the loop, and we pop off the next thing. We're going to pop off this A. And so let's delete that. Oh gosh. I don't know how that happened. Erase? Can I erase this one? No. My PowerPoint hates me today, sorry. So it's going to be slow. But there, pop the A off. We visited A. And I think you get the idea at this point, right? Now we have at the top of the stack E, we're going to go back and pop it off. Bam. Because we've seen it, right? We have seen it, and so we're not going to follow that if statement. We've got all this stuff going in there. Okay, and so there's that. E is happy. And so then we have A again to pop off. And so we're going to pop off the A there. I wonder if I can use... I'll just use the eraser again with my mouse. It's not happy with me. So we're pop off the A. And again, all right, has A been visited? Yes. So we're not going to deal with it anymore. So we're just going to keep going back and popping off things until it's something we haven't seen yet. And so now we get to the C, right? We finally get to the C here, and it's our turn. Our turn to push that C. So now it's C that we're going to look at, and we're going to pop it off. Ooh, it erases now. Who knows why? So we got that one. So now we just popped off C. We have not seen C before, so we're going to visit it, add it to the visited set, and we're good to go there. So add C there. It was the 6th thing we saw, I think, right? 6. And we saw it, the way we got there was through A, if you remember. A pushed B, C, and E. We still got the B down there still. But that's how that one worked. And then, all right, we added it to the visited set, push all of its adjacent vertices into S. So we're going to push A and G. Those are the two things adjacent to C. So A and G. There we go. And then, all right, G's at the top now. We're going to pop it. G has not been visited, so we'll visit it. And then, so it was the 7th thing we saw. We saw it through C. And now we'll push all of its adjacent vertices. If we're at G, the only adjacent thing is C. BAC. So C's at the top of the stack, and we're done. And so now we're back at the top of the loop. And now we're just gonna, like, we've seen everything. We've seen the whole graph at this point, right? So we're just gonna keep popping stuff, and we've already visited them, so we're gonna keep skipping the loops. We're gonna pop C off, skip this part. Then we just go back to the loop. Pop A off, skip that part, right? Pop B off. And now the stack is finally empty. Once the stack is empty, depth first search, or DFS, is done. It's done its job. It's visited every node. But do you see how it went deep first? It went like through E, like did a weird roundabout way. It went as much as it could without having to retrace its steps. It went all there, right? That was as deep as it could go. And then it's like, all right, I give up. I have to backtrack. And so it backtracked, and eventually it saw the C and the G line. So that's how that worked. And so you can kind of draw like who discovered whom, and this actually creates a tree if you think about it long enough, if you remember what trees are from 41. But we'll talk about that a little bit more in the next set of slides. But yeah, this idea, I think you can imagine that we can fix that. That's a bit of a waste. Like we can just push the things that aren't already visited, because like we're going to skip it anyway if it was. So that's definitely a speed up. But yeah, this is depth first search. It discovers the graph from a starting vertex, and it runs in size of E plus size of E time. So that's the first one I want to show you. The next one I want to show you is breadth first search. These are hard to pronounce. So depth first search, breadth first search. So depth first search starts and goes deep. Breadth first search goes wide rather than deep. All right. So, and the only difference, honestly, it's the same algorithm. It's just instead of a stack, we use a queue. Remember those? That's pretty cool. That just one gives you the other. So yeah, if you just replace the stack with the queue, it will stick as close as possible to the starting vertex for as long as possible. It'll just like grow its little discoveries slowly but surely. All right, it's not going to get too deep in the graph. So again, same running time. It's just because stacks and queues take the same amount of time, right? They're both constant to push and pop. So yeah, everything's the same, but we can also fix this. We can make it a little bit faster. We can say, all right, let's just push all of these unvisited adjacent vertices into the queue. That will make it better, okay? It is a queue this time instead of a stack. So let's do the same thing. Let's do breadth first search on the same graph, starting from A, and so let's watch it work. So again, visited set starts out empty. It's a queue now, all right? And it's also starting out empty, and we're going to push our starting vertex to the end of the queue, right? That's how that works. So A is at the end of our queue. We'll draw it like a list again, where the front of the queue is on this side and the end of the queue is on this side. The front is the end right now. And so now, while the queue isn't empty, let's pop it. So we'll pop that A off. And then we haven't seen A, so we'll visit it, as usual. It's the first thing we saw, because it's the start. And then we're going to push all of its unvisited adjacent vertices to queue. Well, actually this time, for once, all of its adjacent vertices are unvisited. So we're going to push B, C, and E to the end of the queue each time. That's how you push to queues, right? And that'll make all the difference. Watch. So, all right, now we're moving on. So the next thing we're going to do is we're going to pop this queue. And actually, I'll draw the queue a little bit differently this time. I'll just keep everything we had before. So like we had A, we popped A. We popped A and we added its children. Or not its children, its adjacent vertices, B, C, and E. All right, so now this is what the queue looks like. The real start is B now. A is gone, but just I'll draw it to show you what was there. So B is at the front now, and we'll pop B. All right, B has not been visited, so we'll visit it. It's the second thing we saw. We saw it through A, and let me draw that a little bit better. We saw it through A, and we're going to push all of its unvisited adjacent vertices. So we're going to like not have to worry about A anymore, right? So we'll push the D and the F. I'll just push them in alphabetical order. Okay, so that's what we're going to do there. And yeah, we're going to keep on trucking now. So back to the top of the loop. So we're going to pop the Q, and notice that it's going to pop the C now. It's just the older things. The older things are getting visited first, and those happen to be the immediate vertices that are adjacent to A. So you see how those are the ones we're going to care about first, and those are the ones we're going to discover first. We're sticking close to A at the start because of the way that the Q works. So now we're popping C. We have not seen C before. So we're going to visit it, add it to the visited set. It was the third thing we saw. And we got here through A, if you wanted to remember that. All right. And then we'll push all of its unvisited adjacent vertices, which is just G to the Q. It's the end of the Q. And so we have to deal with everything that was already there first, because Qs get, like, they're first in, oh gosh, first in, first out, right? That's the technical term for it. So we have a bunch of work left to be done from before. We're doing it in that order. Okay, so we push that G, and now it's time to go back to the start of the loop. So we're going to pop our Q, which is going to get the new thing out. That's the E. We popped the E. We did not see E before, so we're going to visit it, add it to the visited set. It was the fourth thing that we saw. We saw it through A. All right, push all of its unvisited adjacent vertices to the Q, and it looks like it's F. Though we will see it before when we get to this one. So it will be, you can still have duplication in the Q, but that's okay, even with this improvement. So yeah, let's keep on trucking. So now we've seen 4 things. That's good. So now we're going to pop the Q again. We see D. We're there. We have not seen D yet, so we're going to visit it, add it to our visited set. And visit is whatever you want it to be. Maybe it's like you're looking for the end of a maze, right? And once you find it, you're kind of done. You wanted the path how you got there. So there's D. We saw D through B, didn't we? 5th thing. And we'll push all of its unvisited adjacent vertices, but there are none. We've seen B, so we're good. So we go back to the top of this loop, pop F. We've not seen F yet, so we're going to visit it, add it to our visited set there, and it is the 6th thing that we saw, and you see that we saw it through A. And so this is like this kind of looks like a tree, right? Hope you can see that. So that's happening. And let's see what else. We'll push all of S unvisited adjacent vertices, which is nothing, because we've seen B, we've seen the E. Those are the 2 things adjacent. So we're good there, and so we're just back to the start. So pop it off. We have G, popping that G right there. And all right, we haven't seen it, so let's visit it, add it to our visited set. And we saw this one through C. That's our 7th thing that we saw. And we'll push any of its unvisited adjacent vertices into the Q, but there are none. We've seen everybody at this point. So yeah, that's everybody. Everybody's happy. I can close it off, and we're good to go. I hope you see that. All right. So yeah, at that point, we're just back to the top of the loop one last time. So we have F being popped, but F is in the visited set, so we're just going to skip it and now go back to the start, but the Q is empty, so we stop the while loop. And so that is breadth first search. And do you see how it's not going as deep? Like it's not doing this. It's not doing this like depth first thing. It's doing a breadth first thing. So it's kind of doing this. It's like stick as close to the start as possible. Like it's building its feelers out in this way. And then it's like, all right, then take another step for each of those. Take another step. It's kind of looking like a normal looking tree, right? So it's visiting all these, then all of these, then all of these in that order because of the way that a queue works. All right. And so that's exactly the same as like a breadth first tree traversal. If you remember that, it did use a queue. I taught that in my 41 class. But yeah, that's a thing. Maybe you've heard of it before. It's the same for graphs, essentially. It's using a queue, right? Depth first search using a stack. That's the only difference there. So those are two very important algorithms to discover, like to search for stuff, to like go through everybody in the tree. It's a graph traversal. It's a way of traversing the graph, visiting every vertex, doing something. Maybe you're searching for a way through your maze, for example. And let's say you wanted to like get from the start to the end of this graph the fastest. How would you search for that? Depth first search would like get lost in the weeds, right? It would like try to go as far and long as it can in the graph, and that wouldn't really lead to the exit in a very fast way. Breadth first search would actually be probably the best option for getting through this graph, this maze, getting from start to end, because it like explores slowly but surely. It's guaranteed to find the shortest way to get from S to E, so that's pretty nice. So along those lines, there's another algorithm that has to do with weighted graphs. So say like it costs some money to go through this graph. You want to spend the least amount of money to get from somewhere to somewhere else. Let me teach you an algorithm called Dijkstra's shortest paths algorithm. So it was invented by a man named Edgar Dijkstra. He was super, super cool. And the way it works is that instead of a stack, or instead of a queue to look around, if you replace that, both of those, with not a normal queue but a priority queue, remember that? So that's implemented using a heap data structure, which has like costs associated with things. It's getting the minimum thing out, right? Or the maximum thing out. We're going to care about the minimum in this example. That'll help you find the shortest paths in a weighted graph, like the shortest way to get from, I don't know, let's say A to D or something, because it's not obvious, right? Because if you mess up the weights, like maybe this isn't the shortest way anymore. Like maybe this is a better way. You see that? If the weights were different. So yeah, it's a hard problem, and it's really, really solved beautifully in this algorithm. So what happens in Dijkstra's algorithm is that you give another starting vertex, just like we've been doing, and the algorithm will find the shortest path, the shortest way, and it'll tell you how to remember how to get to every other vertex in the graph. All right, so it'll remember, like, so starting at A, let's say, it'll discover all the shortest paths to get to every one of the other nodes in this graph. It'll find the way with the minimum cost. It's really nice. All right, so the running time of this algorithm is a little bit worse because you have to, like, queues and stacks, they're like constant time to do stuff, right? If you do a priority queue, that was like logarithmic time, if you remember that. So you have to like multiply your operations by a log. So it's size of E plus size of E times a log on the number of nodes in the graph, because like that's the maximum that would exist in the priority queue at once. You wouldn't add any extras, no duplicates. So it'll be that time, but you can actually do a little bit better with a fancier data structure that we're not going to go into because it's way too complicated. But this is still a pretty good time, right? So it's invented again by a man named Edgar Dijkstra, who I think he was Dutch, and he's super, super cool, absolute legend. And I'm not just saying that because I'm kind of like, I'm related to him technically in my PhD journey. I'm not like by blood, but by knowledge. So he was my PhD advisor's PhD advisor's PhD advisor's PhD advisor's PhD advisor. So I am technically in the genealogy of like professors. I am related to him in that way, which is kind of cool. So yeah, there's a lot of cool stuff that you would use this for. Like just imagine like Google Maps is using this all day long to tell you how to get somewhere from your house. And yeah, this is a really cool graphical introduction to Dijkstra and the algorithm. And so I encourage you to look at this if you're interested. It's a very cool algorithm to understand and get good at. So here's the algorithm. It's going to look a little bit different. Honestly, it's more or less the same. But the things that we're putting in the priority queue have to do with like the amount of like, have to do with like the length of the path, the length of our shortest path so far. So we have to remember some extra stuff. All right. So we're going to have to hold on to some more variables, but it really is just like push the starting vertex to the priority queue instead of like a normal stack or a normal queue, and just like, well, the priority queue is not empty, pop it. Okay. But here's what's working. All right. What we're going to do, we're going to have a visited set again. We're going to have two new things, two new maps. All right. These are going to be like hash tables, you can imagine. They're maps, key value pairs. So we're going to map nodes to distances. We're going to make a map called dist. It's going to give us the distance from our starting vertex to this vertex that we're caring about. So like we can ask for what's the distance from our starting vertex to A or something. We can look it up in the map, and that will tell us. And then we'll also make a predecessor map called pred, and that's going to map nodes to other nodes. So like that's going to remember where I came from along my shortest path. So the person before me, my predecessor in the shortest path, like you can ask for the predecessor of the E node, and maybe you can store C into there. So it's a map from nodes to nodes. So like if you're programming this, you could use node pointers or something. And then yeah, now we're going to use a priority queue. So we're going to make an empty priority queue. It's going to be a min priority queue because we want the shortest distance, not the largest distance, right? And the first thing we're going to push is our starting vertex, but like that has no number associated with it, does it? So the thing that we're going to push to our priority queue is not just nodes, because like those have no numbers to minimize, right, associated with them. We're going to push pairs of things. We're going to push pairs of starting vertices, or we're going to push pairs of vertices and where we came from and the distance that we got there. All right, the distance that it took us to get there. All right, so it's really not a pair, it's a triple, I guess I should say. So that's what we're going to push. We're going to push 3 things at once. All right, vertices, another vertex of where we came from, and then a distance that it took us to get there. Okay, that's the idea. And so I'll explain that more later. For like, how do we get from the starting vertex? Where do we get from? Let's just say that we came from the starting vertex. This is just like a dummy value, silly default value. You can give like the null pointer if you wanted to. But you got to give something. And yeah, the way that this is going to work is like the predecessor map and the distances are going to work together and say like, oh yeah, the predecessor of E was C, and so like we came from C to E. Maybe the predecessor of C was A, and so it's going to like show you how you got there, and the distances are going to be minimized along the route. Okay, so yeah, this is what we're going to keep doing. So we're pushing triples of things, 3 things at once: vertices, previous vertices, and distances, distance estimates to our priority queue. 3 things at once. So every time we pop it, we're getting 3 things off, right? A node, where we came from, and the distance. All right, so that's what we're doing. So we're going to pop the thing, and this is the distance. This distance is what we're going to minimize in the priority queue. That's what's going to be minimized. That's the idea. So we're always popping the node with a min distance value inside that priority queue. All right, and then if it hasn't been visited, we'll look at it, and then we're going to deal with like how to mess with the distance and predecessor maps, and then push things. And we have to like update. We have to remember where we came from when we're pushing things now. It's not just push the node, it's push like, how did we get there? What is our distance estimate to there? So I think an example will make the most sense right now. So let's do that. Let's have this one, and for fun, let's start in a different place. Let's start at the D node this time. So let's say that we're going to start at the D node. I'll highlight that. So we care from here. We want to find the shortest path from D to every other node in this graph. All right. And the way we're going to build it up is in this dist and pred stuff. All right, that's the idea. That's where we're going. So let's do it. Let's do it together. So all right, initially we have an empty visited set. Boop. We have an empty priority queue. We have an empty map, empty distance map, empty predecessor map. So I'll just draw them as lists of pairs and things like that. And then the first thing we do is we push to our priority queue our starting vertex, which is going to be D this time. It's a triple of things. Starting vertex is D. Where we came from, prev set to starting vertex just for fun. It could be set to null or something if you wanted it to be. And then the distance, what's the distance from our starting vertex to itself? Well, that's 0. You don't have to go anywhere at all. You're already there, right? So this is your prev part, and this is our dist part, and this is the number 0. Maybe I should just draw that better. And of course, my mouse is unhappy. Or my pen tablet is unhappy. My mouse is fine for some reason. It's able to erase. So dist is 0. All right, so that's my thing. And so, all right, now we're ready for the loop. So while PQ, our priority queue is not empty, we're going to pop off the thing. So I'll just like, I don't want to erase that. So we're going to pop off V, previous, and distant to V. So those are the things I'm getting. D, D, and 0 right now, the distance to V. And all right, if I have not seen that thing, I have not seen D before, so I'll add it to the visited set. It's the first thing I saw. So there it is, D. All right, and then I'll update, because this is a good guess, right? It's the minimum thing. I'm popping off the node with a min distance. There is just one thing right now. The min distance was 0 to D. So all right, that's what I'm going to update dist and pred to. All right, so dist, the minimum distance to V. We have a good estimate for it right now. That's going to be whatever we just popped off. So 0. So the distance to the D node, we're going to map D to 0 in our map, right? Dist is a map from nodes to distances. So we'll map that to 0 because that was the min one right now. That's the one I just popped off with the min distance. It better be the good one. And then we'll say where we came from to get there. So the predecessor of D is, we'll just say D itself, or you can just say like null. But we'll just know once we get to the start node, like don't keep traversing. So that's not a big deal. And then, all right, for each of these adjacent vertices that have not been visited, because the second they have been visited, that's going to be the minimum. We're good. So, all right, it's just B. We're going to push that, all right? And so we're going to push that to the priority queue, B, right? But we're also going to push those other two things. Where we came from, right? We're going to push the previous part for B. That was D. It's set to V, right? V is the thing I just popped off. So it's D. D is where I came from. That'll be the previous node along the route if this was the better route. And then the distance to get there from the start is the distance from the start to the V, which was this, which was 0 for us, right? Plus the weight of that edge that we followed to get to this node. So here we were at D, where we noticed that B existed. It was a neighbor. It was unvisited. And it took 5 units to get there. And it took 0 from the start of D, right? So it's the 0 plus 5, weight 5, right? 5, the distance is 5 to get there. That's what you add, okay? And so this is the number that's going to be, we're going to be minimizing that when we have multiple options. But right now it's just another one where we have no options. So we're back at the start. We're going to pop this off. So this is the number 5, right? Pop this off. And so it's B that we're going to look at now. We have not visited B, so we do all of this. So we got B going on in there. And all right, that was a good one then. So all right, the distance to V then is going to be the thing that we saved. So it was 5, the thing that we popped off. That was our min distance to B. So that was the best way to get there. And then the way we got there was from the predecessor. So that's D. That's the thing that we got out and put in there. So the predecessor of B along the shortest path to get to B was D. See that? That's how we're doing that. And so then we noticed like this was the shortest path to B. We did that one. We did this one. And then we're going to push all of its unvisited adjacent nodes. All right. We're going to push A and F. Those are the two things that are there. See that? So I will push, let's see. Let's do F first because it's closer. F. And then the order doesn't matter because we're popping it off in min order, right? So F, we got there from B. And the distance to get there was the distance to B, which was 5, right? 5 is what we got. And then plus the 3 to get to F. So that's 8. If that's the best way to get to F, it would have taken 8 if we took that route. See that? So that's 8. That's one thing we need to add. Then also we need to add A. So we need to add A. We got there through B. And the weight to get there would have been the 5 to get to B plus the 8 to get along that edge to A. See that? So it's 5 plus 8, so 13. And so now, finally, we're back at the start of here, because that was all the things we needed to push. So the priority queue is not empty, and now we have 2 options. And we're going to pop, because it's a priority queue, we're going to pop the thing with a minimum weight. So it's like 8 versus 13. 8's the winner. And so this is the best way to get to F, apparently. F is the winner right now. So we're going to pop that off, and all of its weights and its predecessors and things. And so we haven't seen F yet, so we'll add it to our visited set. And we'll remember how we got there. So the distance to F, the shortest path distance to F, is 8. That's what we just popped off. And then the way that we got there was through B. That was the lucky way to get there. So the predecessor in the shortest path to F was B, the B node. All right, and then you push, as usual, you push all of its unvisited adjacent vertices and their like how we got there, and their distances. So that was F that we followed to here. See that? And then we're going to push all of its adjacent vertices that have not yet been visited. So E is looking just like E right now. And the way to get to E is, if we take this route, E through F with weight, well, to get to F, it's 8. To follow this path from F, it's 9 to get to E. So that's 8 plus 9, so 17. And I think you can see there might be a better way to get there. I can't really tell. It's either this way or this way. Actually, this might be the better way. So we'll discover. We're going to show that we have options eventually. And so now we're back to our priority queue. All right. So now we're back to the top of the loop. Now we're going to pop the one with the minimum weight. It's going to be the 13, right? And so it looks like we're going to visit the A node. We're going to look at the A now. All right. Have we seen A? We have not. So let's go and visit it. Visit the A node and remember how we got to it. So let's see. The distance and the way we got there. So it was 13. Distance was 13 to get to A from the start along the shortest path that we know about. And so that's 13. And we got there. The predecessor of A in the shortest path was B. All right, that's what we're saving there. All right, and so then we just noticed A, and we got there through B. So there. Then we'll push all of its adjacent vertices. So we'll push the E and the C. See that? I guess I'll do C first. So I'll push the C through A, right? And what's the weight? So A, 13 to get to A, plus the 6 to get to the C from A. So 13 plus 6 is 19. And then also E. We have the E. If you go through A, it's R13 to get to A, plus the 7 to get to the E. That's 20. So yeah, it is a little bit better to go through F, isn't it? And we'll notice that. The priority queue is going to notice that right now. Okay, so now we're back to the top of the loop, and we'll pop it. We'll pop the minimum thing. So it's 17 versus 19 versus 20. This is a priority queue, so we're popping the 17 for sure, right? So we're going to visit the E, because it's not been visited. So we'll visit that E. We're good, and we got there through this one. It was through F. So this is the way that we got there, and so let's mark that. Let's remember everything. So we'll add the distances and the predecessors. So all right, apparently the shortest path from the start to E is 17, so we'll save that. And then also, the way that we got there, the predecessor was, predecessor of E on the shortest path was F. Okay, so that's that. And now we're just going to keep on trucking. So we'll add all of its adjacent vertices that have not been visited, E, but we've seen A, we've seen F, and so we're good. Don't have to add anybody. All right, so now we're back to the start of the loop. While it's not empty, we're going to pop the minimum thing, so 19 versus 20, we're popping that 19 and visiting the C node. All right, so we'll visit that C node, and it has not been visited, so that is going to be the shortest path. So C node, we'll add it to the visited set first, of course. We got there through the A. Isn't that nice? And, all right, what was the shortest path? The shortest path distance was 19 from the start. And then the way that we got there, the predecessor of C was the A. That was the best way to get there. There are other ways, right? You could have come this way to get to C, but that was a longer route. And we discovered the shortest one. So we came there through A. All right, and that will allow us to recreate that shortest path. All right, and then we're going to add all of its adjacent vertices in the right way. So, all right, it looks like it's just unvisited thing is G. So we'll add G to our priority queue. We could visit G through C, and the way that we got there is 19 plus the 1 to get to G, plus the weight of that edge. So that's also 20, okay? And so now, back to the start of the loop, we could pop these in any order, right? Because it's 20 versus 20. It's just arbitrary which one you get first, because we're always popping the minimum. They're both the minimum, so it doesn't matter which one you pop. It's still going to be a correct algorithm. And so let's pop this one, and we're going to look at E, and E has been visited, so we just skip all that. Back to the start. Isn't that nice? And then we pop the G in one last iteration. So we'll pop it, and G has not been visited, so we'll add it to our visited set, G, and that's the last one. So the distance there was 20 to get to G from the starting vertex, and the way that we got there along the shortest path was through C, apparently. All right, and then we'll push, if there are any, so we got G through C, and we'll push any of its adjacent unvisited vertices, which would just be C, but C has been visited, so we're good. So don't push anything at all. And then now, go back to the start of the loop, but the priority queue is completely empty. We visited everybody, and so Dijkstra's algorithm is complete. And what has it done for us? It has discovered the shortest paths, and I kind of drew them for us, if that matters to you. It's discovered the shortest path to all of these nodes. So really I should have drawn arrows here, but the predecessor map is telling you, just kind of the opposite way, how to get to the starting vertex. All right, so let me show this to you. Let me show you, like for F, for example. This is the predecessor map is remembering the shortest path. So like, let's say I want to know, I've run Dijkstra, I want to know the shortest path from the starting vertex to the F node. So in the dist map, you know that the starting vertex to F is going to have distance 8, and then here's how you read and use the predecessor map. So starting from F, you're going to look it up in the predecessor map. F maps to B, so B was the predecessor along that route. And then you go and you look up B in the predecessor map. What was the predecessor of B? And you see that it was the starting node D, so that's where you stop. So Because if you follow D again, it's like D goes to D again. Like that's useless. And so these were predecessors of each other. So really it was this order. D, then B, then F. That's how you get there. That was the shortest path, and it had weight 8 total. Does that make sense? That is really cool. That's Dijkstra's shortest path algorithm. It works for most weighted graphs, and it's super, super cool. That's going to tell you, like, if this was a street map, it's like going to give you the fastest route with the least amount of work to be done. Isn't that neat? So yeah, really, I don't know if I should be drawing these arrows, like, I should be like arrowing these if I wanted to be, but I think you get the idea. So like, we're never going to follow this edge, for example. There was no need to. It was too much effort to go all that way out. So yeah, that's the Dijkstra's shortest paths algorithm. It's very, very cool, very, very powerful and useful. It's just another way of searching through a graph, though, isn't it? So yeah, I have one last algorithm I want to show to you. Not really going to test you too hard on on Dijkstra or this maximum flow algorithm, but it's something I want you to see. It's useful. So this is the last thing that also I want to talk about today about graphs, and it also has to do with weighted graphs. All right, weighted graphs, just like Dijkstra's shortest paths algorithm, but this time it's a weighted graph with direction. Excuse me, that's the way I want to say that. With direction this time. So in addition to like street maps, weighted graphs can model some other things. They can model like pipes and the flow through a pipe. Like you can send 10 units of water this way or this way. 10 units for Fresno, 5 units for Clovis or something. I don't know. That's probably how things work. Electrical supply lines. I can send this many volts along this wire, this many volts along this wire, and then also just networks of computers. Like I can send 10 gigabits this way, 5 gigabits this way, and like the weight along those directed graphs this time represents how fast things can flow. All right, how fast things can flow. And I think you can imagine, like, I would like to, like, if I own these pipes or something, I'd like to send the maximum amount of water through it so I can, like, make money. I like to, like, use my network to its fullest potential. I want to send as much information through it as possible. So tell me how to route things, and so I can make more money, right? Again, usually it's about money. So the weight represents how fast stuff could flow through this. And so we'd like to maximize that kind of flow. And so with a graph like this, there's an algorithm. It's called the Ford-Fulkerson algorithm. It's very famous. It's going to find the maximum flow possible if it's set up like this. If there's a source vertex, we're going to call our source vertex S, to a sink vertex. So this is our source vertex. We're going from here to here. Okay? We're trying to send stuff out through. Everything's coming out of there and everything's going into this one. And the idea is, like, how much stuff can you send to T? Can you get the full 15 amount? I think there is a way, right? Do you see how if you you could send the full 10 along here, send 10 along this one, 10 along this one, send the full 5 along this one, okay? And then you can only send 5 along here. You got 10 coming in, right? 10 going in. You can take 5 of that and move it out to here. That's fine. Take the 5. And then, right now, there's only 5 coming into this node. You could send 5 out, but that wouldn't be the full flow. Here's what you can do, right? You take this 10, you split it up into 5 coming out here, and then another 5 coming out of here, because this one has the capacity to hold 15. You send 5, because that's all you got, and so now you got 10 coming into here, and so you can send that 10 right out. And so you can maximize the flow, and you can get the full 15 if you divert 5 out through here. You see that? Does that make sense? That's what I'm trying to say here. That's the goal here. So send the full 10 that way, send the full 5 this way, take 5 of that 10 here, 5 of that 10 here, and then you can get the full 10 out of this one. And that's what you wanted at the end of the day. Okay? I hope you see that. And so, yeah, this algorithm is going to tell you which way to send stuff, how to do it. It's going to be a greedy algorithm, if you remember that from CSCI 41. So it's going to make a greedy choice that, like, locally looks good to it, and that will end up giving you the true maximum flow by the end of the algorithm, which is pretty nice. You just do the thing that looks right to you, and it's going to work out. Okay? So here's the algorithm. Let me show it to you. There's a lot of moving parts. It's best explained with an example, just like Dijkstra. But these are good like larger algorithms for you to get used to, because this is going to be exactly what you're going to do in a 4-year college's algorithms class. You're just going to stare at these all day and like try to understand them and why they work and analyze them. So here's the Ford-Fulkerson algorithm, and it takes a few things, right? It's going to take a bunch of capacities, right? It's like this is a capacity along this graph. It can send 10 units of data that way. This has capacity 15 in this direction, right? So that's a capacity. There's got to be a source node, RS, and a sink node, T, all right? So stuff is coming out of here, and we're trying to have it flow all into there as much as possible. We want the maximum flow, all right? And so the output of this algorithm is to determine that flow from S to T of maximum value, all right? And so let me just read it, and then I'll draw pictures, okay? So you're going to start off sending nothing through all your edges, right? The flow for everything is 0. Start off with nothing, and then while we're going to look for paths. While there's a path from S to T in a special graph that's not our original graph. Like this is normal G. This is our normal G graph. I can go back to blue. This is our normal G graph. We're also going to make a graph called the residual graph, and I'll show you what that is in just a second. Don't worry. It's the same vertices but different edges. I'll tell you what that means. And they're going to have to deal with something called the residual capacity, how much you can send backwards, how much can we still send forwards, stuff like that. So we'll talk about that, because you can imagine that there's going to be negative flow in the opposite direction. Well, we'll get there, don't worry. So while there's a path from S to T in that special graph that I'll draw for you, such that there's an edge and there's a way to get there along the graph, what we're going to do is we're going to send the maximum thing that we can through that path that we found. And so let's pretend this is the residual graph for a second. So like this is a path from S to T, right? Do you see how there's 10 and there's 5, but we can only send at most 5 along this path, because like this 5 is the bottleneck. Like this is a big pipe, this is a smaller pipe, yeah? You can only sure you can put 10 through there, but like you can only put 5 through there. So you have to deal with the bottleneck of the graph. That's the idea, all right? So just imagine that. So the bottleneck is that guy. You can only send as much as the minimum thing. So we'll get there. And then what you do is you use that minimum flow and you increment your guess as to what the maximum flow should be. All right? So you do that, and then you also think about the flow in the opposite direction, because you might want to backwash things. And this is going to look a little weird, but you might want to return some of that flow to make it, you might notice a better way to get from S to T if you do it that way. So this is going to be the key right there. But again, it's best to draw it, and by the time the while loop is done, the maximum flow has been achieved. Okay, so let me do this for our graph, for our normal graph, this one. Let's find a maximum flow using the Ford-Fulkerson algorithm. All right, so here we go. What we do is we start off the flow, our guess for the flow, at 0 everywhere. So 0s all over the place, right? So we can send, the capacity for all these was 10, 15, 5 in that direction, 10 in that direction, 5 in that direction. We're going to send nothing right now along those pipes. Okay, that's the idea. And then we're going to construct the residual graph. And so again, what the residual graph is it has edges whenever there's a positive capacity in that direction. So there's the idea of our residual graph, GF, is that we have the ability to send 10 on this pipe, because we're not using this pipe right now. It has the capacity to send 10 right now. You see that? So it really is just the normal graph right now. This has the capacity to send 5. We're sending nothing right now. This one has the capacity to send 15, because we're not using it right now. We could send 15 in that direction if we wanted to. Same for this one. Same for this one. All right. Send 5. Could send 10 if we wanted to. We're not using those pipes right now. We could. And so what we're gonna do is we're gonna find a path from S to T, just any path. You can see that there's one this way, there's one that way, there's one this way. Let's find a path of minimum amount of edges. That'll be useful for us later. So I could choose either this one or this one. They're both of length 2. Let's just arbitrarily choose the top one. So this is our path, right? We have 10 and we have 5. So we have the large pipe, 10. We have the small pipe, 5, to get from S to T. And so how much could you send along this path? What's the capacity of that path? What's the flow along that path? That's the minimum capacity along it. Does that make sense? The minimum capacity along each edge in the path. So you got the 10, you got the 5. The smallest thing is the 5, so it's going to be the 5 that wins out. So we're going to send 5, really, 5 along here. We're going to be sending 5 along here and 5 along here. Okay? And so that's what it says. That's what this says to do. For each edge along that path, we are going to increment this. This is going to become 5, right? We're going to add 5 along this path. So we're going to do that. And then also, if we can, we're going to remember that we could send it back if we needed to, if we discover a better way. So we're also going to add to our residual graph the idea that we could send, like, because we're sending 5 this way, there's a way to send it back as well. We could also send 5 back. Because we're sending 5 this way, we also, if we needed to flush our system and find a better route, we could also send it back. All right? That's what we're going to add. All right? We're going to add that to our flow. We could flow it backwards as well if we needed to. I hope you see that. So that's the idea there. And so then we have a new flow that we've built up so far, and we have a new also residual graph. So it looks like this now. See this? So this is our graph with our current flow. We have 5 in this direction, 5 in this direction now. So we're exhausting this pipe, which is nice. But now our residual graph looks like this. We've sent 5 this way, but we could also send it back if we needed to. If we found a better way, we could do that. That will help. If you get into the nitty-gritty of this algorithm, just doing it in reverse eventually finds the best way if you need to go through that route. And then this one, it's been exhausted in this direction, so if you needed to, you could send that 5 back, but you can't send any more from U to T in that direction. Okay? So this is our new graph that we could use to augment our flow. All right? And so again, we want to do, while there's a path, let's find a path from S to T in this graph, in our residual graph. And it looks like there is one. There's a couple, right? You can go this way, or you can go this way. Let's find the one with the minimum amount of edges. And so we'll do this one plus this one. That gets us from S to T. Notice that there's no way like this anymore, because we've exhausted this pipe. We can only go backwards right now. Okay, so let's use this path. And so again, it's a pipe of size 5 plus a pipe of size 10. How much could you send along this full path? It's just 5, right? Just 5 is the minimum. So that's the flow along that path, and we're going to augment our flow using that 5. So this edge is going to get 5 added to it. We're going to take 5 more, add it to the flow, and then this edge is also going to get 5 added to it. So we can send 5 this way, all right? And so then, now in our residual graph, we can send 5 backwards. We can send 5 back that way, and we can also send, because we sent 5 this way, we could also send it right back. So we're going to see that on our graph. We can still send 5 more, because this one has the capacity to send 5 more. You see that? So that's what our new residual graph is going to look like here. So now we've updated it. So we still got the flow from before, the 5 on this one, the 5 on this one. And then we've sent 5 this way as well. So 5 on this one, 5 on this one. And so using this, how do we construct our residual graph? It looks like this now. So we've sent 5 this way. You can also still send 5 back. We've sent 5 this way. So there's no more that you can send in that direction, but you can send the 5 back. And then same for this one. Like, we've sent all the 5 that we could in that direction. You could send it back if you needed to. And then we've sent 5 this way, but there's still 5 you could send. Capacity was 10. And then because we sent the 5 that way, we could send it right back if we needed to. And then again, we're going to look for a path from S to T. So it looks like there's only one way. Can't use this one. Can't use this one. There's only one way to get from S to T right now, and it's this roundabout way, the purple stuff. And so that's our last way to get there right now, as far as we know. It might update as we do more things, but all right, that's our new best way. So there's a path from S to T, and all right, let's find the bottleneck. So it's 5, 15, and 5. 5 is winning out. So we're gonna send 5 along each of these. See that? Because that's the amount that we could augment the path by. So all right, for each edge, we're gonna add that capacity to our flow there. And then we can also send it back in the opposite direction if we needed to. All right, so again, let's see. We're going to augment this by 5, so we're adding this. Now this is 10. Now we're sending 5 that way, and then we're sending 10 this way. All right, so how is that going to mess with our residual graph now? Now we've sent the full 10 this way, can't send any more, so you can only send the 10 back. We've sent the full 5, so you can only send the 5 back. we've sent 5, so you can still send 10 more. You can still send 10 more, but you can still send the 5 back. All right, so we're going to add those kinds of nodes to the residual graph. So here's our current flow network, 10 out of 10, 5, 5, 5, 10 here. And then here is our residual graph. So we've sent the full 10 in this direction. You can only send it back. There's no way to get from S to U in that direction. Same with this one. Like, there's no way we sent the full 5 in that direction. All we can do is send it back. There's no more we can send along that original direction of the pipe, right? So that's what the residual graph is representing there, which is a cool little idea. And then, yeah, this is the only pipe that has not been used to its max. And there's honestly nothing else we can do. We can send 10 more in that direction if we needed to. Send 10 more, and then we sent 5 in this direction, so we could send the 5 back if we wanted to. And so, is there a path from S to T now in our residual graph? No, there's no way to get out of S now because only things are coming into it. So that means there's no more ways to get from S to T. There's no more ways to augment the flow and make it better. We actually have the maximum possible flow now, which makes sense. Like sending out 15 and sending in to T 15, that's as good as we can do. You can imagine in different graphs, like maybe you couldn't send as much because like you had smaller pipes or something. But yeah, we were able to send and get the full flow from the source to the sink, and this was how. All right. And yeah, Ford Fulkerson told us exactly what we needed to do, how much flow to send along each path, which is really nice. And once it stops, there's no more ways to add to the flow, which is really nice. All right. So again, I'm not going to like test you on Ford Fulkerson. It's a harder topic, but it's a really cool one, I think. Right. So let's talk about its running time really quick. It's a little complicated. So if you do what I was doing and you find your path from S to T as like a shortest, not Dijkstra shortest, but like shortest number of edges path, if you use breadth first search to do that, then if you use breadth first search to find your path from S to T and just pick one, the first one you find, that will become what's called the Edmonds-Karp algorithm. So for some reason, 2 last names became 2 other last names, which is silly. But the running time of that algorithm is size of E times size of E squared. Just the E is the squared thing. Okay? And the reason for this, we can try and analyze this together if you want to. The reason for this, if we go back here maybe, is that each iteration of the while loop is going to take O of E time, size of E time, right? And let's talk about that. Because, like the breadth first search, you can imagine, because the graph is connected, the edges outnumber the vertices, so the amount of time to do this kind of search, that's going to take, I'll use green maybe, the amount of time it's going to take to do this kind of search while there's a path. So just looking for that path, that's going to take O of E plus V time, right? That was the time for breadth first search, but like there's way more edges in this connected kind of graph than vertices, so it's O of E really to find the path, and then just to do the body of this loop, it's going to loop through at most edge size of the edges. It could potentially go through all the edges because like this edge, this path, like went through the entire graph somehow. Yeah, that's a possibility. So you might have to affect, right? This is just like the length of the path could be the number of edges in the graph. That could be OV. And then also for each edge could be like at most it's all of the edges. See that? And it's doing constant work. Like this is just adding to the flow. You can just imagine that's updating a map at constant time. So yeah, it is O of E per iteration. And then to get the rest, the loop itself, it's going to run this many times. Size of vertices times size of edges times for a very complicated reason. You're going to have to wait until a 4-year algorithms class to get the good explanation. But the idea is that each edge that you use in Ford Fulkerson, it's going to be placed in the residual graph, and you're going to use it O of E times, all right? You're going to use it at most O of V times, which is weird to think about, size of V times. Because, just imagine, like, do you see how, like, here's a good example. At the start, we used this edge. We used this edge, and it was a length 2 path that we needed to get there. The next time we used this edge, we were coming along a larger path, okay? this is not the foolproof. I'm not really saying it right either. But this is like the hand-wavy idea of what's happening. Like, it gets harder and harder to get from S to T along the same edge. So the most that edge can reappear is like the most, how many times can you make this path longer? If it's going to always get longer, it's v times, right? Because the longest path you could have is size of v, right? Just use all the vertices. So each edge could appear that many times, and so you end up with that kind of amount of times the loop runs. You will learn the right way to prove that in an algorithms class, but that's my hand-wavy way of saying what's happening this time. Okay, so that's forward Fulkerson. I'm not going to like test you on exactly what's happening, but this is a good complicated algorithm, just like Dijkstra, to like really get a feel for why people care about graphs. Like, this is a cool problem to solve. Like, we're saving money, putting stuff, we're using our network to the fullest, for example. So yeah, that's where I want to stop for graphs, and I will see you in some new slides next time.